Hello everyone, welcome to Machine Learning and Data Analytics Workshop. Today we will discuss about modeling and training, specifically in regression and classification. So before that, we want to introduce ourselves. My name is Nelson.
And I am Steven, and now we're going to start our workshop.
So first, let's discuss about what are we going to discuss today. First of all, we have what is machine learning. Secondly, we are going to discuss about different types of machine learning, specifically in regression and classification.
After that, we're going to discuss the characteristic of each models, and lastly, the model evaluation.
So, what is machine learning? Machine learning is a subset of artificial intelligence, which provides machine an ability to learn automatically without explicitly being programmed. So we know that traditional programming has been known to solve some of the complex problems for quite some times. But what makes machine learning so special? Actually, even though traditional programming can solve numerous of complex problems, now there are more problems that data reliant. Means that we need another way to solve our problem. And thus, it turns out that many of statistical models are suitable to solve our need. Okay, so now let's discuss about the types of learning algorithms in machine learning. So there are mainly three types of machine learning algorithms that we are going to discuss: supervised learning, unsupervised learning, and reinforcement learning. So first, let's discuss about supervised learning. Supervised learning is a way that we have a data set that contains an inputs and both the outputs. So we have the inputs or features and our outputs or labels. So our main goal in supervised learning is to learn a function that can map the input to a specific output. And that function itself is called a model. So later on, we can predict an output by just having an input passing to the model. And then, one of the main features of supervised learning is that it is quite popular nowadays, as many of the problems in our real life can be solved using supervised learning.
Okay, so the next one is unsupervised learning. In unsupervised learning, the algorithm can naturally detect or infer natural structures or patterns in the dataset without any specific label. Unsupervised learning is especially useful in exploratory data analysis, as it can find clusters of data that have similar structure to each other. Then we can try to make sense of the defining feature of each cluster. So the main difference between those two are supervised learning is done by having prior knowledge of the output values.
Lastly, let's talk about reinforcement learning. So reinforcement learning is about making decision. So let's say we have a software agent that we are trying to create a decision planning. So on its environment, we need a certain rewards value that can make sure the agent can make the right decision based on the environment. So reinforcement learning is currently used for playing games, and actually we are just going to give the reinforcement learning agent what are the rules of the game. And currently, one of the popular games that have been used with reinforcement learning is chess, and one of the agent is called AlphaZero from Google. And we can see that most of the board games that is played by AlphaZero, it has a performance that exceeds the human levels. So now, let's discuss more about supervised learning, as our main topic today is about regression and classification. So, as we mentioned earlier, supervised learning, we have both inputs and outputs, which is the labels. So first, let's talk about both regression and classification. But later we will discuss more in depth about what is regression and classification. So for now, let's just discuss about the main difference between those two. In regression, we use that to predict a continuous output rather than a discrete Boolean types of data, which is yes or no. So if it is a Boolean types of data like yes or no, usually we use a classification. For continuous output of data, usually we use a regression types.
Okay, so in this slide, we will introduce you to regression. An example for regression is to predict the value of stock prices because the stock prices is a real number. One of the models for regression is linear regression, which is the one to the left. It simply finds a straight line that minimizes the distance between the red line and the blue dots. The function of the equation of the line, let's say y equals mx plus b, we can call this the model. Meanwhile, the red line is the output of the model. The blue dots here are the original dataset. We can observe that the red line is optimal because the blue dots are close to the red line. The other model is polynomial regression. Not all data can simply fit a straight line. Therefore, we need a more complex model. For polynomial, we can take account powers of the same or combination of each feature. Therefore, we can learn more complex trends of the data. But we cannot just use high complexity models because it tends to overfit to the training data, especially if you have little training data. Whether you need a more complex model, it usually depends on the nature of your data set.
Okay.
Now we are going to discuss bias and variance. Let's say you have trained your algorithm, but you only can achieve 70% accuracy. Do you think it's good enough? Well, we cannot say for sure because the input alone is not always perfect, as it cannot always reach 100% accuracy. To determine if your model is good enough, you need to have a baseline. That baseline can be a human expert. If the human expert can predict with 80% accuracy, that means your model is performing poorly. It has high bias. But if the human can predict with 60% accuracy, our model performance has exceeded the expert. That means we can say that it has low bias. Now the next problem. Let's say we already trained our model and it is performing well. It has 99% accuracy. But when you are testing it with new data, which means that the model has not ever seen this data, it only can achieve 60% accuracy. Why is that? We usually call this problem overfitting. Overfitting means that the model cannot generalize well to new data. It can only predict input that it has only seen before, and we will need to avoid this issue. We call this model high variance. We usually want our model to have low bias and low variance. Therefore, we need to trick our model to achieve that. Next.
So now, let's discuss about the model and classification. First, let's discuss about logistic regression. Even though the name suggests that logistic regression is a regression type of model, it is actually a classification type. So why is that? So first, let us see what is the x-axis and the y-axis of the diagram shown in the left. In the x-axis, it shows the data inputs of the features, let's say the weight, and the y-axis show that it is a probability of it is being overweight or underweight. Let's say it's an obese, so if the y equals to 1, then the person is an obese. If the y is equal to 0, then it's not an obese. So first, let's see that in the labeled data sets, all of them are labeled such that the probability is either a 0 or a 1. It cannot be 0.4, 0.5, because there is no such thing as both obese and not an obese at the same time. So how do we make such regression? Well, we use logistic regression. Logistic regression is simply like linear regression. It's just that we apply a certain function, which is called activation function, which can be used to classify the inputs. Now, let's talk more about neural networks. Logistic regression is also a type of neural network, but it's a simple neural network. Now, if we generalize to any types of neural networks have input layers, hidden layers, and output layers, as it can be seen on the right diagram. And neural network is much more complicated than logistic regression, because not only that it has more layers, which means more calculation, means it is more complex, thus it needs more computing power and more time to solve it. That's why neural network is more complicated than a normal logistic regression. Now, let's discuss about another types of classification, which is decision tree and random forest. So first, let's talk about decision tree and how can we read from decision tree. Now, if we look at the next slide, which is about decision tree, I've made a decision tree that can classify whether a person is having a COVID-19 virus or not. So in this example, we need to know that decision tree consists of three types of different nodes. On the top one is called a root node. On the middle one is called just a node, and then on the bottom one, usually at the end of the tree, it is called a leaf nodes. So how do we determine the root nodes? Is that we need a certain features that can exactly split the data equally, not like 50%, but the most features that can split the data equally is the one that we put on the root node. So in our case, let's say it's a diabetes. So now let us read how to read the decision tree itself. So first, we have diabetes on the top or on the root node. Now, if a person is having a diabetes, then we need to check again if the person is having a heart disease or not. So let us go through the heart disease test. So let's say the person have tested the heart disease and actually they don't have any heart disease. So here we can see there's a number 11 and 102. So this 11 means that there are 11 person in our training sets that have a COVID-19 that does have a diabetes but doesn't have a heart disease, and 102 of them doesn't have any COVID-19 but have diabetes and no heart disease. And secondly, we can check for another case. Let's say the person doesn't have any diabetes, and we check if the person have respiratory infection or not. So if the person have a respiratory infection, it says that 95 out of hundreds have a COVID-19 case, and 5 of them doesn't have any COVID-19 case. So that is a basic way to learn how to read a decision tree. Now, let us return to the main slide, and we see that there are random forests. So what's the difference between random forest and a decision tree? So in a decision tree, let's say we have 100 data points. These 100 data points are then fed to a model, which is a decision tree model, to create that decision tree that we just mentioned earlier. But in random forest, it's a bit different. Let's say we take around 80 random data sets out of the 100 data points that we have. So out of the 100, we take 80 of them, and out of those 80, some of them are being duplicates, and this is called a bootstrap data. So this bootstrap data is then, we use that bootstrap data to create a decision tree, and we do that based on our number of estimators or number of trees. So let's say we want to create 5 different trees, then we need to do that 5 times. So after we create n number of times, in our diagram we create 10 different decision tree. Then we can fed our testing data. So our testing data is fed to all of those decision tree itself. And we can see from this diagram that 7 of them is classified as a class 1 and 3 of them is classified as class 2. That means by taking the majority, we can conclude that the input data is actually a class 1 type. Now, let's move on to a trend test bed validation.
So now we're going to discuss twin test validation split. Usually in the machine learning workflow, we first need to separate out our data set. Why do we need to do this? Well, this is a way to test for bias and variance using our dataset. In essence, we need to split our dataset into 3 sets, which is the training set, validation set, and the test set. The proportion of the training set should be the largest one. The purpose of the training set is to learn patterns from the data. This is the only time we're going to use it to train our model. The validation set is to understand how our model generalizes on new or unseen data. It also gives us some intuition on how to tune our model. Finally, the test set is to see how our model performs in real-world situations. It is also used as a test to prevent overfitting to the validation set. In some cases, we might be overfitting on our validation set. That means that it is performing well on the validation set, but not so great on the test set. Now about hyperparameter tuning. Models itself are not usually fixed. That means that it has a lot of hyperparameters that we can change that is independent from the parameters learned from the data. For example, for polynomial regression, we can change the maximum degree. For random forest, we can change the maximum depth and also the number of estimators. Hyperparametric tuning purpose is to find the optimal value of the hyperparameter for the dataset, which will give the optimal result. We usually have an automated way to find these optimal values. The first one is grid search. In grid search, we will try a combination of values within a certain range, but each value have a fixed interval from each other. The other approach is to use random search. Random search also searches in some range, but it will pick out the values in a random order. Lastly, we will discuss about model evaluation, which tells us on how well the model is performing. So in regression, we usually have 3 different metrics. The first one is MSE, which stands for mean squared error. The second one is RMSE, is root mean squared error, and lastly is MAE, which stands for mean absolute error. The ET in the equation means it's the difference between the actual value and also the prediction. The main difference between RMSE and MSE is that in RMSE it will take the root of MSE. Meanwhile for MAE it will take the absolute values. We usually use MSE if we want to avoid outliers. Meanwhile, if we for MAE we can take some outliers.
Okay, lastly, we will talk about model evaluation and classification. So there are mainly 4 different types of metric that we are going to use in classification: accuracy, precision, recall, and F1 score. So as you can see on the right diagram, there is this confusion metric that can actually represent all of the metric that we are going to discuss now. So if you see on the right diagram, there is TN, FP, FN, and TP, which stands for true negative, false positive, false negative, and true positive respectively. So to discuss about the accuracy normally discuss about the true. That means it's the correct prediction. So the formula for accuracy is actually true positive plus true negative divided by true negative, false negative, and true positive, which is the total number of prediction. Secondly, we have precision. So precision is similar to accuracy, but we discard all the negative. So we only take the positive. So it's true positive divided by true positive and false positive. Next, we have recall. Now, what recall is used? Recall is usually used for when we are trying to, let's say we have a fraud detection model, and our fraud detection model should have high recall. The reason for that is that if our model misclassify an actual case as not a fraud, that means the company may lose a lot of money because of that. So we need to consider the recall so that it has a low false negative value or a high true positive divided by false negative and true positive proportion. So that's why the recall formula is true positive divided by the actual prediction, or true positive plus false negative. And lastly, there is F1 score. F1 score here represents the balance between both recall and precision, because our model needs to have both the recall and the precision so that our model can have the balance of both of them.
So
And that
let's
is
jump
the
in
end of
into
our
the
workshop.
notebook.
Thank
So
you.
first, we are going to discuss about linear regression. So we're going to input these 4 libraries, which is NumPy, Matplotlib, Pandas, and Seaborn. Pandas here is to handle our dataset data, and Seaborn is to graph. So first, we're going to generate our dataset. Because we are trying to see how linear regression works, we're going to plot a straight line. Okay, and this is the training dataset, which is a simple straight line with no noise. And after we train the model, we can see that the score is 0, and the parameters is 3.4 for the gradient, and for the bias is 2. And we can compare earlier from the generated model. It is also using the gradient of 3.4 and bias of 2. That means that the learning algorithm here can identify the model, the data quite nicely. So let's say we're trying to add some noise to the dataset, and you can see that there is some noise here in the line, so it's not a straight line anymore. And we will try to train the model, and we have a score, an MFC score of 100. It is quite low, but not as low as 0 earlier. This error is due to the noise from the data, and the learn parameters is also different now. And we can observe more in this plot. We can see that the orange one is the predicted one from the model, and the blue one is the original dataset. Yeah, and then we go into the multivariate dataset. So in our previous example, we are only using one dimension to predict a label, but in real-world scenarios, often we have more than one feature, and this is very often the case. And we're going to predict our feature, our label from these features. And thankfully, because we are using SciKit-Learn, we can support higher dimensions easier. So we are going to use this dataset. It's called the California housing dataset, and our objective is to predict the housing price. So firstly, we are going to load the dataset from a CSV file which is called housing.csv, and because our dataset has some missing values, we're going to solve this by dropping it, and we're going to see that our first values is like this. We can see that the majority of our feature is numerical, and this will be our label later, and there's one feature that is categorical, because like the machine learning algorithm only accepts numerical features. We will deal with the categorical feature later. Okay, so first we need to separate our label first, because like our label is the median house value, so we separate it into Y, and this is the values. After that, we're going to separate the features. First, we're going to deal with the numerical feature first, and after we separate it, we can see that this is all the numerical features. And after that, we're going to train our model. We're going to use this linear regression class from SciKit, and after we fit into this model, we have a score of around 70,000. The MSE score of 70,000. This might sound high, but when compared to our pricing, this is around hundred of thousands. So 70,000 doesn't mean that much. Okay, but this is so for now we're going to test if we have this input, what kind of value what kind of value can we expect. So this is just a sample of 2 rows, and this is the value. So if we have this input, we can expect a value of 35,000 to 250,000. For this kind of value, we can expect 238,000. And we can also compare, because we took this from the original dataset. We can see that the actual value is 268,000, and it is quite similar, 192 and to 228. Okay, so but what can we do to improve the score? One of the ways is to encode our missing column earlier, which is ocean proximity. So this is called the data preprocessing, because we're going to process the categorical data into numerical data, which the model can process later. So we first can see that the categorical, this column has this kind of values. So there is only 5 options, which is near bay, less than 1 hour to ocean, inland, new ocean, and island. And we can see the sample for the first five values. This is near bay, and thankfully, to process this numerical categorical feature, we have this thing called one-hot encoding. And in pandas, we have this function, it's called getDummies. What it is essentially doing is that it will make a column each for the values here. So for near bay, it will also have 1 column for itself. For less than 1 hour, it also have 1 column, and it will try to read if the row has near bay, it will indicate 1 over here. That's why it's called one-hot encoding, because only 1 is encoded as 1 here, and then the rest is 0. Okay, so this will be done to the rest of the dataset. Besides preprocessing, we also can add some features ourselves. So if we know some domain specific knowledge here, we can try to add it. So let's say we want to add the total number of bedrooms per room, the population per room, the population per household. Let's say that this kind of features can help to increase the score, and we can find out later. So first we're going to concatenate it all into the columns. Yeah. After we have these values, we're going to concate all the columns that we have computed earlier. The first one is the numerical one, second one is the ocean, and lastly is the handcrafted one. And we can see the resultant data set. So the first columns are the numerical ones, the next 5 is the ocean, and lastly is our handcrafted feature. And we will train using this data set. And the procedure is also the same, and we have the RMSE score of 68,000, which is quite an improvement when compared to the previous one, which is around 70,000. So we are trying to prove that by adding the one categorical feature and also the handcrafted columns can improve the score here. So now we're going to demonstrate hyperparameter tuning. So for this case, we are going to show you a polynomial dataset. We first set the degree to be 3, so we know that 3 will be the optimal value. Okay, and we can see that this is the resultant dataset. And first, we need to separate our dataset into the testing and training. The training dataset will have a 70% of the whole dataset, and the test will be 30%. And after we plot, this is the training one. As you can see, there is a general trend of the polynomial here. This kind of line, and also for the testing set is shown here. Okay, so this is just a helper function to add the polynomial features. First, we need to create the features that has the polynomial features. For this case, we set it to 3, and after we run it, for the training set, we have an MSA score of 600, and this is the resultant plot. The predicted value, which is in orange, which is a quite smooth polynomial, and it captures the general trend of the data. For the test set, we have a score, an MSC score of 782. It is quite higher from the training set, but this is acceptable. And this is the, if you compare to the testing dataset, we will have this plot. So now, what if we set the degree to be 1? So if we have the degree to be 1, that means that this is an ordinary linear regression, and you can see that the score is 1600, which is, if you compare to earlier, it's only 600, almost 3 times. So the linear regression doesn't fit the data well. So this is just an example, like if we are not using a complex enough model, it will give a high bias model. So now we're going to demonstrate if we vary the degree, what will happen. So from the left side, we have the degree of 1, 2, 3, and going up to 9. As we can see earlier, if our degree is 1, the bias will be high, the score will be high here, over here. But as we increase our degree, the score will slowly decrease, and it will reach its optimum value of when the degree is 3, and the score is 1600 here. But if we try to increase the degree more to 9, let's say, we can see that the training will generally go down, but for the testing set, it will go up. So this is the thing that we want to avoid. This is called the overfitting. So around 5 to 9, it is already overfitting. We should avoid the large distance over here. So we want to have the smallest difference between the testing and the training, which is 3. In this case, we have 3 for the degree.
Okay, so now let's continue on to classification. So before that, we need to create a function that can graph a contour function. So here is a plot contour function, and we don't need to care about all of this inside here. As we will see later on, we're just going to use this as a plotting contour function. So now let's start with logistic regression, and here I'm going to import a data set from the SciKit-Learn datasets, which is called a make classification dataset. So first, I'm going to create a dataset. X, y is equals to the make classification with number of features 2. So we will see that we should have 2 different features, and these 2 different features are x0 and x1, and the y here represents the label. So if we see here, this is the first 5 samples of the data, and we can see if we plot everything in our contour map. Before that, we're just going to see in our xy graph. So first, x0 represents the first features, and x1 represents the second features that we have, and the color represents the label. So here we can see that the blue, which is 0, is on the right side, and the orange one is on the left side. So now we're going to start using our logistic regression. So we create our own data frame from both of the features x0 and x1. So x is equals to x0 and x1. Then we're going to use our logistic regression. So here LR is our logistic regression, and we're going to fit to the data. So the data is x, and dfy means we're going to see the labels inside here. So now we're going to see the accuracy of our logistic regression. And the accuracy is 1 as expected, because the data is quite organized in such a way that you can create a line that can split this data equally. So if you see, we are going to use our plot contour that we mentioned earlier, and here we can see that the yellow line represents a probability around 0.5, the blue represents the probability of 1, and the red represents the probability of around 0. So here we can say that the probability from 0 to 0.5, which is 0 to 0.5 here, represents that all the data lies in this area or in this region is 0 as expected. It is 0. Similarly, above 0.5 to 1 is represented as 1. So in this case, our logistic regression is able to determine the data quite nicely. Now, for our second case, which is a neural network, we're going to import a different types of data set. In this case, it's a mixed circles. So we will do the same thing, and we can see in our scatter plot that x0 is our first feature, x1 is our second features, and we can see that there are two different types of circle. In the inner circle, it is classified as class 1, and in the outer circle is classified as class 0. So now we're going to use our neural network, or in this case we are going to import MLP classifier. So MLP here stands for multi-layer perceptron classifier. So first we are going to include both of our features, which is x0 and x1, into our data set x, and then we're going to classify both of them with our labels, which is y. So we need to create our model first. So our model should consist of a learning rate, a hidden layer, and a max iteration. So let's discuss one by one. And usually the parameters that we can change are these three of them. So first of all, the learning rate is the rate where when we are doing a stochastic gradient descent, which is one of the algorithms in a neural network to make sure that our model actually converges into a certain points. And when it converges, it will classify, usually it will classify the model to be the best model in our case. But we need to consider another case, which is the number of hidden layer. So these two are normally the parameters that we can tune. And for number of iteration, usually we want our max iteration to be as high as possible, so that our model can converge. But if we put it too low, or if we put it too low, then it may not converge. And if we put it too high, then it may have a longer time to process the data, and our computer may not be able to handle it. So that's why we need a certain value where the data set will converge. Our model can converge. So now when we fit our model to the neural network, we can see that the accuracy is quite high, 0.95. And we can see that here it classifies all the inside here is classified as 1, and the red is classified as 0. So more or less the classification is quite correct in this case. And now let's compare it to using logistic regression. So if we classify our data sets here using a normal logistic regression, we can see that a logistic regression performs quite poorly in this case with accuracy less than 0.5, so it's unable to accurately represent the label in our data sets. So that we know that we are not going to use, in this case we are not going to use logistic regression for this type of data sets. Lastly, we have decision tree. So we will import another type of data sets, which is make moons, and we can see that moons are created here. This is the blue one is labeled as 0 and the orange one is labeled as 1 with the two different distinct features, x0 and x1. And we can see that this is half of the moon and this one is the other half of the moon. So now we're going to use decision tree classifier. So decision tree classifier, we need to import from SciKit-Learn.tree. So when we import decision tree classifier, we do the same thing, which is creating the data sets of the inputs features x, and then we are going to use decision tree classifier with one of parameters that we can change, which is the max depth of tree. So let's say we are using 3 depths of the tree. So here we can see the accuracy is 0.94, okay, which is quite okay. And we can see that the way that decision tree creates their decision boundary is by creating a rectangle. So here we can see this is the first one and this one is the second one. So each rectangle that it creates represents the number of depths. So here we can see that it creates 3 different rectangles, 1, 2, and 3. So since there are 3 different rectangles, it represents the number of max depth. So it's actually represent the number of splitting when you are doing a max depth, represent the number of split in decision tree. So now we see the counterpart, which is the random forest, where we are using the same data set, and we will see that actually random forest classifier has 2 different parameters that we can tune, which is the max depth as well as number of estimator. Number of estimator here represents the number of different decision tree, as we explained earlier. So here, when we are using the same data set, we can see that the accuracy is a bit higher, but it doesn't represent anything in this case, with the same number of depth of tree, which is 3. So we can see that overall, we can see there are more rectangle because we have hundreds of decision tree, and it's a bit hard to represent the data from and the model from this case from using our plot contour. So we need to know that there are limitations in our plot contour function, especially in random forest, as it is a bit hard to determine whether the models can fit exactly to this data set here. Okay. And that's all for our presentation. Thank you.
Thank you.